This week I'm going to be going over Lab 4A, our standard geometry test and hardness of steels. So this is an ASTM standard. So the ASTM geometry bar test here we can see is the ASTM standard A255-07. So if we want more detailed information on this, we can reference back to that. And this you can find right either on the ASTM website or even just Google this standard and it'll pop you up to the documents you'll need for this. So we can see above here we have all the specified dimensions for the test up here. See our specimen goes right here in the center. So this is a standard measure for hardenability of steel. For our specimen, it's going to be a 25.4 millimeter diameter, 100 millimeter long test specimen that we're going to use for this. Now, the specimen is going to be heated up above 950 degrees Celsius for about an hour. The specimen is then quenched in a water jet here, and you can see the water spray coming up here in order to quench our specimen. And there again is our specimen right there that meets these dimensions over here. So that's a basic overview of this ASTM standard for the geometry bar test. So we can see in the chart shown here, we have the estimated cooling rates within the bar. So if we take a look over on the left-hand side, this is the left-hand side of the bar that is water quenched at the bottom where the water jet is, and the right-hand side over here is the top where it's air quenched there. And we can see our x-axis here is our distance starting at 0 away from the end of the water quenches is all the way up here to 32 over here, where these increments are in 1/16 of an inch. On our y-axis over here, we have the cooling rate, which is in degrees Fahrenheit per second. So as we can see here, we can follow the chart here. The further we get away from our end over here towards our air quench side, our cooling rate is decreasing in this manner here. So if we look at this kind of cooling rates for the bar, as far as the chart goes here, a little T-chart here, we can see our distance here, which is in inches. And this is the relationship between the cooling rate and the distance here. So we got a distance of 1/16 inch. Our cooling rate in degrees Celsius now per second is 315. And again, as we get further away here up to 32/16 over here, our cooling rate drops all the way down to 2.2 degrees Celsius per second. Next, we'll talk about hardenability. So this is defined as the depth of useful hardness which can be produced for a given quenching condition here. It does not relate to the degree of hardness produced here. So we can see here, if we take a look at the graph on the right, if we see our hardness on our y-axis here and our distance on our x-axis here, the further we get away, we can see our hardness decreases. And if we look at this as far as a Rockwell C hardness scale here, and on our y-axis and our distance from the quenched end here in inches, we have a graph that looks like this. So we kind of start off and it's a nice steep slope as it drops off pretty quickly as we get up towards 3/4 of an inch or so away from the end, and then it kind of levels out a little bit more from 3/4 of an inch on. One thing to consider is which type of steel you're using. So right here we have in table 12.1 here compositions for selected steels here. So here's your number, your AISI, SAE number over here, and kind of the percentage makeup for each of these different types of steels. Now there is an effect of alloying elements on the hardenability here. So we can see this in the curve here. So we're using the same Rockwell C hardness scale on our y-axis and distance from the quench end on our x-axis here. So we can see for these different types of steel, 4340, 4140, 2340, and 1040 as different standard types of steel alloys here. We can see as we start off here, when we're right at the end here, I have a hardness on the Rockwell C scale of 60, and you can see the 1040 drops off in hardness much quicker, almost down to about within the first half inch here before it starts leveling out here. Where the other ones, if you take a look at the other end of the spectrum here, are 4340. It stays level and is more of a mellow change as you get further away from the distance from the quenched end. So in this chart here, we show the hardenability for alloying elements here. So you can see you have the different elements for all the curves here on this chart. And down here on our x-axis, we have the percentage of each of these elements, whereas on the y-axis, we show the multiplying factor. In this chart here, we take a look at the relationship between hardenability and the carbon content. So we can see over here we have our hardness again still on our y-axis over here, and our distance down here on our x-axis from the quenched end, given this time in millimeters here. And what we have in the figure itself is the effect of increasing the carbon on the hardenability here. So you can see we have 0.3, 0.4, 0.5, 0.8, and down at the very bottom here are 0.2. So in this slide here, we're looking at an iron-iron carbide phase diagram that's shown. So we're looking at ferrite, which is a BCC or a body-centered cubic form of iron, and austenite, which is a face-centered cubic structure. So larger interstitial site allows for more carbon in our FCC. So up to 2.1% by weight, which we look back over here. Here's our 2.1% over here. When solubility of carbon in Fe is exceeded, we're going to see the formation of cementite down here. So cementite down here, Fe3C, is going to be formed when the solubility of carbon in the iron is exceeded. So this is, you can see here, 6.67% weight carbon down here. So if we follow that right down to there. So in this diagram here, we have our austenite and our ferrite. So austenite again, face-centered cubic, ferrite, body-centered cubic here. So you can look back over at our graph on our x-axis down here where we have our percent weight of carbon. On our y-axis over here, we have our temperature in degrees Celsius. Now, you can see right here we have a question where they're going to ask us at what percentage of carbon will ferrite be formed. So we can go over to our graph over here and take a look at ferrite and see which percentage of carbon on our x-axis this will be formed at. And we can see this is going to be below a 0.035% carbon if we were to check that out. So we have a couple of images in this slide here. Now we can see that the nuclei of the ferrite form at the grain boundaries. So grains grow, shifting from a face-centered cubic to a body-centered cubic at this interface. This is going from austenite to ferrite. Looking again at our percent weight of carbon versus temperature graph here, zoomed in again now here from 0 to 2. What we want to look at with this now is we have eutactoid reaction, and we can see this occurs at 723 if we come over here to our y-axis degrees Celsius for a weight of 0.8 percentage of weight of carbon here, which we come down to our x-axis right here. Remember, if we take a look over here, we can see ferrite forms with a 0.035 percentage of weight of carbon. And cementite forms here, if we recall from a couple slides ago from the larger graph here that went out to 7, this occurs with a 6.6% weight of carbon. So the carbon in austenite goes to the cementite, and the iron in austenite goes to ferrite. And the result is a pearlite. So what is pearlite? Pearlite is a two-phase layered structure composed of alternating layers of our ferrite and cementite. So this occurs in some steels and cast irons. So we can see here in our diagrams, in diagram A, we can see these different layers here. And this shows the redistribution of carbon in iron. And in B, we have a photomicrograph of the pearlite over here that we can see in this image here. And we note the scale down at the bottom here of 25 microns. So in this slide here, we can see is how our method of cooling the austenite here can kind of affect what structure we're going to have afterwards. So if we do a slow cooling, we can see we form perlite here. If we do a moderate cooling, we have bainite, and a rapid quench here is martensite here. So if we reheat this, then we can get a tempered version as well. And we can see in the diagrams here what the structure looks like between the different types of cooling. So now we're going to discuss our bainite and martensite microstructures here. So bainite consists of ferrite plates separated by restrained cementite spheres. And we have our now martensite here, which is very hard, and this is going to induce a BCT. So this is a body-centered tetragonal crystal structure of ferrite and cementite. So if we look down here, here's our FCC, our BCC, and now our BCT structures down here, and we can kind of see the difference between all of these. So if we're talking about martensite here, this results from a diffusionless solid-state transformation, displacive or athermal transformation, or a phase transformation that occurs via small displacements of atoms or ions without diffusion. Now talking about the body-centered tetragonal unit cell, BCT, there are few close packed planes, few possible slip planes, and this is brittle, since dislocations cannot freely move within the grains. This is similar to an HCP or a hexagonal closest packed structure. So on this slide here, we're going to take a look at the complete isothermal TTT diagram for eutactoid composition 1080 steel. See, we have our time down here on our x-axis and our temperature up here on our y-axis here. So a TT diagram stands for time temperature transformation diagram. It is also called an isothermal transformation diagram. So this TTT diagram shows the time required for transformation to various phases at constant temperature, and therefore gives a useful initial guide to likely transformations. So now we're going to take a look at the continuous cooling diagram and microstructure for eutactoid steel. So a continuous cooling transformation, or CCT, phase diagram is often used when heat treating a steel. So this represents which types of phase changes will occur in material as it's cooled at different rates. So stability of phase during continuous cooling. So we can see here we have our austenite here, and denoted down below here is a transformation occurring during cooling by this symbol here. So we can see that symbol right there. So there's our transformation austenite there into perlite there, and then another transformation here. This goes into a coarse perlite when it crosses that line. So what is the difference between this coarse and fine? Well, slow cooling, here we see perlite, so we have coarse cooling here, which is less than 1 degree per second, and fine cooling is approximately 10 degrees per second. We can see the difference in these structures here in the photomicrographs. So A on the left-hand side is our coarse, and B on the right-hand side is our fine structure over here. And you can see this is the same scale on both, 10 microns. So now we can see the difference over here if we look at the continuous cooling diagram for a fast cooling here. So again, same thing, we have our time in seconds down here, our temperature in degrees Fahrenheit on our y-axis here, but now we can see how our graph changes as we're off over here to the right here when we're talking about our fast cooling. Now for fast cooling, we have our bainite and our martensite here. So for bainite here, we're talking about cooling at approximately 100 degrees Celsius per second, and for martensite, the cooling is going to be greater than 140 degrees per second here, and we can see the difference in the structures here. So if we look over at the left under electron microscope at the bainite here, we can see our scale is 1 micron at the bottom. We can see our martensite in this structure up here. We have our cementite right there, and in between here we have our ferrite. So now if we talk about the outline for our experiment 4 for lab 4 here, materials that we're going to take a look at and test are going to be our 1018, 1045, 4140, and 4340 steels. Now this lab is going to be broken into 2 weeks, week 1 and week 2. In week 1 we're going to do the heat treatment and the water quenching and air quenching. And then in week 2 we'll move on and do the hardness, or the Rockwell and Vickers hardness testing. Only one lab report is going to be due at the conclusion of both of these weeks. So over here we have our diagram as well that we've referenced before in previous slides, again with our composition for percent weight of carbon on our x-axis and our temperature in degrees Fahrenheit over here on our y-axis here. So as we look at our 1018 steel, this is a hypereutectic steel with austenitic temperature near 875 degrees. So we can see here the optical micrograph of the as-received microstructure of the 1080 steel showing ferrite and pearlite. So you can see this over here. Again, we note now our scale here is 200 microns. Now, if we're talking about our 4140 steel here, we can see that our composition for 4140 steel, we have between 0.28 and 0.33% carbon, so it's a low alloy steel. And we can see our other breakdown for the elements here as well for the whole composition. The hypoeutectic steel with A3 austenitic temperature near 845 degrees. So this is for our 440 as compared to our 1080. We can see our micrograph over here. We have our scale of 50 microns. So as of the as received microstructure of our 4140 steel, showing again now our ferrite and pearlite. Now we can go back and take a look at our graph here for hardness versus the distance from the quenched end. So this is our hardenability and carbon content curve here. So we can see our carbon content given by each of these curves here and how those relate based upon its distance from the quenched end and how that relates to the hardness of our steel. So this is the effect of increasing the carbon on hardenability. So now let's take a look at our TTT diagram for 4140. So chromium, molybdenum steels here. So we can see down on our x-axis we have time in seconds. And pay attention to what type of scale this is down here as we quickly go from half a second over here up to almost a full week over here. So pay attention to your units there, and also pay attention to your units on your y-axis here. This is temperature, but we have the option of dealing with degrees Celsius or degrees Fahrenheit. So this quickly becomes important when you're doing your calculations, looking things up on graphs. For your lab, are you dealing with Celsius or Fahrenheit? Make sure to convert between the two if you need to, or if you don't have a graph that contains both of those. And we can see over here on our right-hand side, we have our hardness as well. So now we're looking at our 4340 steel over here. And again, we have our time on the bottom, seconds, minutes, hours here. So on our y-axis we have our temperature. Now it's only giving it to us in degrees Celsius over here for this particular graph, but we still have our Rockwell hardness on our right-hand side. So that's another thing to pay attention to with your units is what units are they dealing with? They're dealing with Victors, which Rockwell scale, all that information. Make sure we are looking at the right units, the right scale, and the right equations and calculations for this. So in this week's lab, we're going to be doing the quenching and tempering of the 4130 steels for tensile testing for our later lab in 5A. So we're going to talk briefly here on heat treatment of our 4130 steel. So what we're going to do is we're going to heat this and maintain it at 925 degrees Celsius for a little over an hour. Then we're going to rapidly quench in a water bath. So if we take a look over here on the right in this image here, the quenched specimen, we can note that there's a scaling on the surface resulting from oxidation. Now we're going to talk more on quenching and tempering treatments in a couple of weeks when we get to our next lab, Lab 5.